This is a short lecture about chemical bond energies. And as a quick review, chemical bonding is an electrostatic attraction, which simply means the attraction between two oppositely charged particles. And so bonding is an electrostatic attraction between two atoms. The driving force behind bonding and chemical reactions in general is that atoms attain a complete full outer shell of valence electrons, which in most cases is 8. The octet rule. So there are two basic types of bonds that we've talked about. There are more than that, but the two primary ones are ionic bonds, which result from complete transfer of valence electrons to yield ions that are electrostatically attracted to each other, and the sharing of valence electrons between two neutral atoms, and the electrostatic attraction in that case is between the electrons of one atom and the nuclei, the positively charged nuclei of another. So as I just kind of said verbally, for a covalent bond, the electrostatic attraction is between the electrons of one atom and the nuclei of the other. And so bond energy, which is a primary theme of this lecture, is how much energy does it take to break that electrostatic attraction and pull those two atoms apart. We've mentioned bond energy curves before, but I just want to emphasize it is important to understand them and be able to interpret them. A bond energy curve has energy of the system along the y-axis and bond length or internuclear distance between the two atoms that are bonding along the x-axis. And so, as all things in nature, the most stable configuration is at the lowest energy. And remember here that negative energies are preferred. That simply means that the more negative the energy, the more stable the system. And so you can get some good information from the bottom of a bond energy curve. If you drop from that point to the x-axis, you will get the bond length. And so the bond length for this graph would be 74 picometers. If you go from the bottom of the energy well over to the y-axis, you can get the bond strength, okay, which in this case is negative 432 kilojoules per mole. So bond strength is the bond energy. Okay, it's the amount of energy that needs to be put in to break that bond or break the electrostatic attraction or separate those two atoms. Okay, they all say the same thing. And so the distance between zero energy is the two atoms when they are not close enough to feel the effects of each other. So bond energy is this distance from 0 down to the lowest point. That's also the energy required to break the bond. Now, as you can imagine, every bond has its own bond energy graph, and you should be able to look at comparative bond energy graphs and interpret the difference between the different bonds. So, for example, let's look at X2, the bond that it's representing. Okay, that particular bond has a bond energy of maybe negative 450, something like that, kilojoules per mole. We can't say anything about the bond length because we don't have an X scale here, okay? But it's relatively short bond length, right? All right, now let's compare X2 to Y2. How do the bond energies compare? Well, the bond energy of Y2 is almost negative 1,000. So Y2 has a much stronger bond, is a much stronger bond than X2. Now, what can we say about the bond length of Y2? Well, the bond length is longer. Let's compare X2 to Z2. All right, so which has the shorter bond, which has the stronger bond? Okay, so X2 and Z2 have about the same bond strength. But what's different about them? Okay, the bond length is different. Okay, X2 has a much shorter bond length than Z2. All right, so just make sure that you can interpret the difference between different bond energy graphs. Now, not shown in that particular diagram, but a general trend, assuming that other variables are held constant, is that as the bond length increases, the strength decreases. That makes sense if you think about it, okay? So if you're comparing a bond, let's say between A and B, and let's do this. All right, so a much shorter bond is typically stronger, and that makes sense because remember, bonds are electrostatic attractions, so the closer two atoms are to each other, in general, the stronger the electrostatic attraction. So that would make sense that short bonds would be stronger, okay, and that long bonds would be weaker. Now, it's not just any random bond. You want to compare similar bonds. For example, this series up here between hydrogen atom and a halogen, okay? So you're not changing both atoms at once. You can see that there's a clear trend here that as the bond length gets longer, and remember, why does it get longer? It's because the halogen, the iodine, is much larger than the fluorine, so they can't get as close together, and the attraction is weaker. Okay, but anyway, so as the bond length gets longer, the bond energy gets weaker, less. Again, holding other variables constant, so let's look at the bond between two carbon atoms. Covalent bonds, of course, we know we can have single, double, and triple bonds. And as you might expect, the bond length of a carbon-carbon double bond is shorter, is less than the bond length of a single bond. And a triple bond is yet shorter than a double bond, okay? But even though the length is getting shorter, the strength, the bond strength is increasing. As you would expect, carbon-carbon triple bond is the strongest of carbon-carbon double bonds, or of carbon-carbon bonds in general. Alrighty, so one thing that probably a fundamental, I maybe even should have put this as the first slide. Breaking any bond requires input of energy, okay? Just like breaking anything, okay? Anything you break, you've got to put in energy to break it, okay? And what our convention for having to put in energy is a positive value. So if you see any energy reported with a plus sign, that means it required the input of energy. And making a bond is exothermic, meaning that energy is released, okay? Because when you make a bond, you're going from a higher energy state. Remember, in order to make a bond, in order for something to happen spontaneously in nature, the driving force is a lower state of energy, okay? So anything that is exothermic, anything that releases energy by convention is given a negative sign, okay? And that's a good thing in nature. All right, so why? Well, it's nice to know bond energies, period, to know how stable something is. But another really useful application of bond energies is to be able to predict the overall energetics of a chemical reaction. What am I talking about? If you have any reaction, so let's just look at this really simplistic, okay? In any reaction, chemical bonds have to be broken on the reactant side, right? And we know that requires input of energy, okay? Bonds broken, big plus sign. And in the product side, typically new bonds are made. Not always, but typically new bonds are made. And we have just learned that as any bonds that are made goes to a lower energy, and that's negative. So if you combine the bond energies from the bonds broken and the bonds made, guess what? You get the overall enthalpy or heat of reaction. You can predict if a chemical reaction overall is endothermic or exothermic, which helps chemists a lot. So here's an example of bond energy. In a bond energy table, all energies are reported as positive. Okay, in other words, they're all reported as the energy required to break that bond. And so you should be able to make some pretty simple predictions as to whether a very simple chemical reaction overall is going to be endothermic or exothermic. We're not actually going to do more complex calculations with this yet. You will run into that later on in Gen Chem, but not just yet. Here is the type of simple example that you should be able to understand and explain. This happens to be the combustion of natural gas, okay? And just to kind of help you visualize it, here are models of the reactants and products. And as I said, in any chemical reaction, you are going to break some bonds. In this case, when we combust natural gas, CH4, we broke 4 carbon-hydrogen bonds. And then looking back at that bond energy table, each carbon-hydrogen bond is 413 kilojoules. There are 4 of them that we broke. So we had to input 1,652 kilojoules per mole simply to break all the bonds in methane, in natural gas. We also had to break the 2 oxygen-oxygen double bonds from molecular oxygen. And again, so that's a total input of about 990 kilojoules. So if we added these together, you would see that in order to break all the bonds in the reactants, we'd have to put in 2,642 kilojoules per mole. However, every bond then that we make on the product side is going to release energy. It's going to give energy back to the surroundings. So here are the bonds we've made in the products, okay? We made 2 new carbon-oxygen double bonds, and we made 2 molecules of water. And if we drew a model of those, we made 1, 2, 3, 4 oxygen-hydrogen bonds. So if we add the energy released to the environment from the bonds made, it shows us that we get back minus 3,450 kilojoules, okay? So now we had to put energy in to break bonds. We got energy back when we made new bonds. What is the net result of those? 2,642 is what we had to put in to break the bonds. 3,450 is what we got back from making new bonds. So adding those together, the net enthalpy or heat of reaction is a negative number. What does that mean? That means that this overall reaction is exothermic. Guess what? We know that combustion, we know that burning things is exothermic, right? Releases heat, keeps us warm, right? So that fits with what we know about combustion reactions. It is, in fact, exothermic. All right, so quick, we're done now with this lecture. A quick summary of the key points you should be getting from this PowerPoint. Breaking bonds are always endothermic. Making bonds are always exothermic. Be able to recognize from a bond energy graph or identify what the bond length and the bond energy is from these graphs. Describe and explain the relationship between bond length and bond strength. Be able to compare two bonding graphs for two different types of bonds and explain which one has the shorter or longer bond length, which one has the higher or lower bond strength. And then use the relationship that I just showed you using bond strength to predict the overall enthalpy or heat of a reaction. That's it.